Hello, what's up, guys? Today we will be looking at container technology and pods in Kubernetes. I have seen many engineers who use containers and interact with containers, but don't know what a container is on a Linux system. Is it a magic? How do we even achieve a container on Linux? After I give you some theoretical background, I will create a container on Linux without using Docker so that you can grasp the idea of container in your mind. First of all, there is no magic in computer science. Everything has to make sense. Let's go to pre-container era and let's invent containers ourselves. In pre-container era, we have our OS on a bare metal hardware or on a virtualization technology like VMware. Now, say I want to isolate a single process running on Linux on a bare metal server. Let's make it a process in a way that it cannot see other processes. It can operate in its file system on its own. It can have its own resources like CPU, memory, disk, or network bandwidth. It's autonomous, which means it can operate in its isolated environment without needing anything else. What is the purpose? Well, if I can achieve such isolation, in that case, I can decouple that process with its environment and distribute or deploy it independently to any platform. It will work in the same way everywhere since it is autonomous and it has all the requirements together. Now let's think about the benefits of that isolation. I can distribute and deploy it independently, which makes microservices possible. Starting up this isolated process is as easy as starting up any process. Compare that with a bare metal server. They have to start whole kernel. Since it is isolated, I can limit the resource usage for that specific process or process group, like how much memory or CPU it can use. As it is too lightweight, I can deploy many of those on a single server. You got the idea. Now let's see how to achieve those on Linux. Actually, similar technology already exists on FreeBSD operating system, which is called jail. Linux has 3 kernel features that makes process isolation possible. The first one is jaroot or pivot root. Jaroot command had been around for decades when we invented containers. It sets your root file system to a given folder so you cannot see anything outside that folder. You kinda get jailed in that folder. Even your root user cannot go upper folders. That's why it is called jail in FreeBSD. You can use jaroot in your Linux box. It's not a container-specific technology. When you have a broken disk or AWS volume that doesn't boot, how do you fix it? You first need to detach it from your unhealthy system to attach a healthy system, and then you can mount it. Now you can jaroot to that mount point. Another Linux kernel feature is namespaces, which helps make isolated processes. With the help of namespaces, you can isolate a mount point for a process or create a network stack only accessible inside that namespace. Namespace can isolate network, mount point, hostname, process ID, user ID, or IPC, inter-process communication resources. That means those isolated processes can have the same process ID or hostname or the same file descriptor for a socket, or they can have their own network interface and routing stack. That's totally fine because they don't see each other's. Third kernel feature we need to achieve our scenario is control groups. C groups provide resource limitation capability. When I say resource, I mean CPU, memory, disk, I/O, or network bandwidth. Okay, enough talking about the Linux kernel. You might be asking, where does Docker fit in this picture? Most people think the container is equal to Docker, but that's not true. As you just learned, containerization is a kernel feature. You don't even need Docker to run a container. All those kernel features come with some command line tools that help you facilitate those features and run a container. Then what is Docker? Why do we use it? Although you can run a container with the available Linux commands, it's not an easy task to manage multiple containers, especially when the containers are ephemeral, short-living. Docker provides tooling to manage the complexity behind the scene. You don't need to worry about lots of details with Docker because you need to set up file system, network, routing, and lots of other details to bring a fully functional container to life. Now we can look at pods. Containers on different hosts can't see each other's by default. They need to bind their host's port because they don't exist outside their world. Only the host is real in the real world. Remember, container was just an illusion. Kubernetes introduced the pod concept as a wrapper around containers. Pod adds a virtual overlay network that makes containers neighbors, as if they lived in the same network while on different host machines. A pod can't contain more than one containers. After this background, we can now talk about the differences between virtualization and containers. Virtualization allows us to run multiple OS on the same host hardware. Those individual OS boxes called guests. Each guest has its own kernel, which means you have to boot the kernel. On the other hand, container is just an isolated process or processes with its own file system. It doesn't have a kernel, so it is lightweight. It can start in seconds. Process or processes inside the container think they are the only processes, and their file system is the only file system. Remember the illusion. But we know they are just in a jail on the host operating system. Thank you for watching my video. Please subscribe to my channel and hit the like button. See you in the next video.